So I want you to picture something for a second. Just imagine a brand new, completely freshly paved freeway.
Oh, like perfectly smooth blacktop.
Exactly. I mean, perfect blacktop. There's not a single piece of debris on the road, no broken down cars, no potholes. Visually, the condition of that road is just flawless.
Sounds like a dream commute, honestly.
Right. But there's a catch. What if that pristine, empty freeway has 10 hairpin turns, a collapsed tunnel right in the middle, and the exit ramp is entirely blocked by a solid concrete wall?
Well, then traffic fundamentally can't move. You have the cleanest road in the world, but your throughput is 0. Nothing's getting through because the physical geometry of the road just prevents it.
And that scenario is exactly how we need to start thinking about dryer vents.
Yeah.
Welcome to today's deep dive. We're looking at the latest data and inspection standards from the Dryer Vent Safety Council.
Yeah, and we're also pulling some really great insights from the industry leaders over at InOvate Technologies.
Right. And our mission today is to completely dismantle this really common counterintuitive misconception. This idea that pulling a massive clog of gray fuzz out of a shiny metal pipe means your appliance is automatically safe and well-performing.
It's arguably the single biggest mistake property owners and even, some professionals make in this industry, assuming that clean equals safe.
So we're going to look at the actual physics of how your home's exhaust system works.
Yeah.
Because we have to separate how a vent looks from how it actually performs.
And I think it's a critical distinction. We're exploring this today not to scare anyone, but really just to look objectively at the mechanics of building science. I mean, we're dealing with a system hidden inside your walls that you probably use multiple times a week.
Okay, let's unpack this, though, because I'm stuck on this right from the start. If I pull a giant clog of lint out of my vent, doesn't that inherently fix the airflow?
Well, removing lint is absolutely essential. We definitely can't understate that. When lint is the source of the restriction, getting it out of there will dramatically improve airflow.
Right. I mean, it feels like washing a car to fix a broken transmission or something. Like, sure, the car looks great, but aren't we still fixing part of the problem?
You are. But the issue is that lint is often just the most visible symptom of a much larger aerodynamic problem. We have to think about what the dryer is actually trying to do.
Which is dry, wet clothes.
Right, but physically, how? When you put wet clothes in the drum, the dryer heats the air to absorb that moisture. That hot, heavy, moisture-laden air then has to be evacuated through the ductwork to the outside of your house.
Okay, makes sense.
So the blower motor in your dryer is really only designed to push that heavy air against a certain amount of physical resistance.
And when you say resistance, you mean the air is literally rubbing against the inside of the pipe.
Exactly. In fluid dynamics, they refer to it as static pressure or friction loss. Every foot of pipe adds a little bit of friction.
Oh, wow. Okay.
Yeah, so the longer the duct, the more resistance the air encounters, which slows the velocity of the air down. And if the air slows down too much, it can't carry the heavy moisture.
It just drops it.
Basically, the air cools off inside the pipe, the moisture condenses, and the lint just drops right out of the airstream and sticks to the walls.
So the lint buildup you're seeing isn't always the root cause of the problem.
No, it's often the result of an exhaust system that has too much resistance built into its fundamental design.
So if I clean out the lint, I'm really just treating the symptom. I haven't fixed the reason the air is slowing down in the first place.
Precisely. A clean duct doesn't magically shorten a vent run that was built way too long. It doesn't straighten out a sharp, restrictive elbow joint hidden inside your ceiling.
Wait, elbow joints? Like the turns in the pipe?
Yeah. Every time you force a column of moving air to suddenly change direction, like hitting a 90-degree turn inside a wall, you create massive aerodynamic turbulence. The air just crashes into the wall of the pipe, causing the pressure to spike and the velocity to plummet. You could have a vent that is completely devoid of lint, but if it has 4 90-degree elbows in a tight space, the blower motor in the dryer is just going to choke.
Wow. What other structural roadblocks are we talking about here? Because if we're looking past the lint, what else is physically stopping the air?
The materials themselves play a huge role. I mean, building kinds require smooth, rigid metal ductwork for a reason.
Right.
If a builder or a homeowner uses corrugated flex duct, the stuff that looks like a metallic slinky.
Oh, yeah, I've seen that behind basically every dryer ever.
Exactly. Well, the air has to bounce over every single ridge inside that pipe. That creates immense friction compared to smooth metal. You might also have a section of ductwork inside a wall cavity that was accidentally crushed by a plumber or an electrician during construction.
Just stepped on it or something.
Yeah. Or you might have a hidden booster fan that has failed.
I actually noticed that in the source notes. Why would a dryer vent even have a fan inside of it? Doesn't the dryer push the air?
It does, but in a lot of modern construction, especially condominiums or townhouses, the laundry room is placed right in the center of the house for convenience.
Oh, right, away from the exterior walls.
Exactly. That means the exhaust duct might have to travel 30 or 40 feet just to reach an exterior wall. That distance creates way more static pressure than a standard dryer motor can overcome.
So they add a fan to help it along?
Yep. Builders install secondary mechanical booster fans inside the ductwork, often hidden up in an attic or a crawl space, to help pull the air through that long run.
But mechanical things eventually break.
They always do.
Yeah.
The pressure switch might fail, or the motor might just burn out from age. And here's the really insidious part.
What's that?
A property owner might buy that condo and never even know the hidden booster fan exists.
Oh, no.
Yeah. When that fan stops spinning, the heavy metal blades inside the pipe stop acting like a fan and start acting like a wall.
They just block it.
Right. They become a massive physical blockage right in the middle of your exhaust system. You can brush out the pipe until it shines, but if you have a dead booster fan sitting in the attic, your performance is fundamentally zero.
This highlights a huge limitation with how these systems are typically inspected. I mean, if cleanliness is just a condition, the instinct for most of us, and frankly a lot of technicians, is just to look inside the pipe.
Sure, they use a flashlight, or more likely one of those flexible scoping cameras.
Exactly. But if I'm understanding the physics here, visual data does not equal aerodynamic data.
It doesn't. And we need to be careful here because scoping a line with a camera is an incredibly valuable diagnostic tool.
Oh, for sure.
Sending a camera down a duct reveals conditions we could never see otherwise. It shows you if a joint has pulled apart inside a ceiling and is dumping moisture into your drywall.
Or where the lint actually is.
Right. It identifies damaged materials and obviously shows you exactly where the accumulation is.
Wait, but isn't seeing believing? Like if I'm standing next to a technician, watching a live camera feed of my vent on a monitor, and the metal walls look perfectly shiny and spotless, shouldn't I feel totally confident?
Well, what's fascinating here is that it's basic human psychology to trust what we see. We suffer from visual confirmation bias.
Okay, explain that.
A technician sees a clean pipe, assumes they've succeeded, and completely ignores the aerodynamic drag of the system as a whole. But think about the physics we just discussed. A camera cannot mathematically calculate the friction coefficient of the materials it's looking at.
Right.
It cannot add up the cumulative pressure drops caused by the length of the run and the multiple elbow joints. It just can't do the math.
It just shows you a picture.
Exactly. A vent that looks completely clean and shiny on a camera monitor can still perform terribly when you actually turn the dryer on because the geometry is fundamentally flawed.
That is wild.
And the reverse of this is also true, which is really interesting. A camera might show a vent that looks visually ugly.
Ugly how?
Maybe the metal has some strange discoloration, or the foil take on the joints looks a little sloppy. Visually, it's imperfect. But functionally, structurally, the airflow might be experiencing very little resistance.
So it's actually fine.
It might be performing within a perfectly acceptable, safe range. Visual information simply answers a completely different question than performance data. Looking at a pipe asks, what is the condition? Measuring asks, what is the performance?
Okay, here's where it gets really interesting to me. It's exactly like going to a doctor for a physical.
Oh, that's a great comparison.
Right. A doctor doesn't just walk into the exam room, look at you sitting on the table, say, well, you look healthy, and send you home. They don't rely solely on their eyes.
Right, they take your vitals.
Exactly. The very first thing that happens, usually before the doctor even enters the room, is a nurse takes your blood pressure, they check your heart rate and your temperature, they establish objective numerical vitals before the visual exam even begins.
That analogy perfectly captures the methodology the Dryer Vent Safety Council emphasizes. Everything has to start with a baseline reading before you decide what the system actually needs. You have to establish the vitals.
And in this industry, how does that happen?
That happens through specific performance measurements using specialized instruments.
Let's get into the weeds on those instruments for a second, because the source material mentions a few different ways professionals actually capture this data. I mean, how do you measure the performance of an empty tube?
There are two primary metrics a technician is looking for: pressure and velocity.
Okay, let's start with pressure.
To measure pressure, they use a tool called a manometer, or a specialized pressure gauge. They basically insert a small probe into the ductwork right behind the dryer.
While it's running.
Yes, when the dryer is running, this tool measures the static pressure, essentially how hard the air is pushing back against the blower motor because of all that resistance down the line.
Got it.
It's usually measured in inches of water column. If that number is too high, it means the motor is fighting a losing battle against friction, bad geometry, or a blockage.
And the other metric is velocity.
Right. They might use a tool called an anemometer at the exterior termination.
The outside vent.
Yeah. This measures how fast the air is actually moving, usually calculated in cubic feet per minute, or CFM. It tells you the actual volume of air successfully making it out of the house.
Which is the whole goal.
Exactly. The specific tool a technician uses is really less important than the philosophy behind using it. The principle is simply to get a baseline reading.
Get the data.
Give yourself objective, mathematical data about what the operating system is actually doing, rather than guessing based on what the inside of the pipe looks like.
Which brings us to the core diagnostic loop outlined in the research. Measure, inspect, diagnose, service, and measure again. Walk us through how that loop actually plays out in a real-world scenario.
Sure, let's follow a textbook scenario. A technician arrives at a property and starts getting that baseline reading. The pressure gauge indicates a really high level of static pressure. The system is definitely not performing within the desired range.
So they've established what the system is restricted.
Right. Now they have to figure out the why. This is where the visual inspection comes in. They scope the line with a camera and find a massive wall of lint about 10 feet into the ductwork.
Okay, so they clean out the lint, the pipe looks shiny, and normally this is where a less experienced technician packs up their tools and hands you the invoice.
And that's exactly where the danger lies. Because our technician is following the full diagnostic loop, they don't just rely on the shiny pipe. They turn the dryer back on and take a second measurement.
Oh.
Let's suppose that second reading shows the pressure has dropped a little bit, but it still falls well outside the safe operating range.
The needle barely moved.
Exactly. If you hadn't measured, you would have looked at the empty pipe, assumed you fixed the problem, and left a serious fire hazard inside that wall.
Wait, really? Just left it there?
Yes. But that second measurement tells the professional something vital. It tells them the lint was only part of the problem. It wasn't the whole story.
The data demands that they keep investigating.
Exactly. Maybe the effective length of the duct is simply too long for the dryer's capacity. Maybe there's a crushed pipe hidden behind the drywall that the camera couldn't quite see clearly. Measurement tells us how the system is performing. Inspection helps us determine why.
So cleaning is a service, but diagnosis is a process.
That's a great way to put it, yeah.
So if the gauge still shows high pressure after the main duct has been thoroughly scrubbed, that resistance is backing up from somewhere else. And based on the sources, the culprit usually isn't hiding in the middle of the ductwork at all.
No, it really isn't.
It's at the absolute extremes of the system, the very beginning and the very end.
It's one of the most common oversights in the entire field. It's so easy to obsess over the hidden ductwork inside the walls while completely neglecting the exterior termination.
The actual exit.
Right, the exact point where the air is supposed to leave the house. You can have a perfectly clean, perfectly straight run of pipe, but if the exit door is jammed shut, you still have a failing system.
I mean, it's like paying for ultra-high-speed fiber optic internet, but the cable plugs into a 1990s dial-up modem on the side of your house.
Yes.
The middle of the line is absolutely perfect, but the termination ruins the whole thing.
Yeah.
Let's talk about those exterior terminations, because the ways they fail are actually pretty fascinating. What goes wrong at the end of the line?
Well, the most common issue is the introduction of screens. A homeowner or, a pest control company will notice birds or mice trying to get into the warm exhaust vent, so they just install a wire mesh screen over the exterior cover.
Which seems logical.
It does, but building codes specifically prohibit screens on dryer vents for a very good reason.
Because it turns into a lint trap immediately.
Instantly. When that hot, wet lint hits the wire mesh, it doesn't just pass through, it sticks.
Oh, wow.
The moisture causes it to basically cement to the wires, and within a matter of weeks, it forms a papier-mâché brick that completely seals off the exhaust. The dryer motor is now just blowing against a solid wall.
What about the covers themselves? Even without a screen, they have flaps, right?
They do, usually lightweight louvers or a single damper flap designed to open when the air blows and close when the dryer stops, just to keep drafts out.
Those break.
They do. The mechanical parts fail, the hinges rust, or an overzealous exterior painter might accidentally paint the louvers shut, literally gluing them to the frame.
Oh, man. I can totally see that happening.
Oh, it happens all the time. And if the termination is low to the ground on the side of the house, landscaping mulch, overgrown bushes, or packed snow can just completely block the airflow.
And a lot of these vents go through the roof, right? That seems like a whole different set of problems.
Roof terminations are notorious for ruining performance. A specialized dryer roof jack has a specific damper designed for low-pressure exhaust.
Okay.
But when a homeowner gets a new roof installed, the roofers often just rip off the specialized dryer vent and replace it with a standard attic ventilation cap.
Wait, why would they do that?
Because they look similar. But those attic caps have built-in screens and heavy metal baffles. The roofer thinks they're doing a great job keeping the rain and the squirrels out, but they've just functionally crippled the dryer's ability to breathe.
It's incredible to think about. I mean, you could pay for a full duct cleaning, watch the camera feed show a spotless tube, but the air is just violently crashing into a heavy metal baffle on your roof.
Exactly.
The pressure backs up, the velocity drops, the lint starts building up all over again, and suddenly your dryer takes 3 cycles to dry a single load of towels.
That's exactly the cycle of failure. And the exact same principle applies at the absolute beginning of the line, too, right in the laundry room.
You mean right behind the dryer?
Yeah. The transition duct, that's the visible piece connecting the back of the dryer to the wall, is often the weakest link in the whole chain. People use cheap, non-code compliant foil slinky ducts, and then they push the heavy washing machine and dryer tight against the wall to save space.
Which instantly crushes the duct into a pancake.
Right. You've created a massive choke point before the air even enters the wall. And, we haven't even mentioned the appliance itself.
What goes wrong there?
Sometimes a technician will clean the entire vent line, verify the terminations are perfect, measure the pressure, and it's still bad. Why? Because the dryer's internal blower wheel is packed full of lint, or the motor itself is failing. The infrastructure is fine, but the appliance just isn't generating the velocity required to push the air.
All of this really drives home why that final step in the diagnostic loop measure, again, is basically non-negotiable.
It really is.
The cycle can't end with the cleaning service. It has to end with proving the service actually worked mathematically. So what does this all mean for the listener? If the second measurement barely changes, does a good technician just shrug and leave?
Definitely not. Comparing the before and after measurements under consistent conditions is the only way to know the job is actually done.
Right.
Best case scenario, after you unkink the transition duct, clean the pipe, and remove that bird screen from the roof, that final measurement shows the system has moved from poor performance into an optimal range. You have undeniable mathematical proof that the system is breathing freely.
And from a property owner's perspective, that changes the entire dynamic of hiring a professional.
It really does.
Most of this infrastructure is buried behind drywall or up in a dark attic. You can't see it, and you don't know if it's safe. Instead of just taking a technician's word for it, that they did a good job because they showed you a pile of lint on the floor, you can actually look at the gauge and see the hard data. The numbers don't lie.
It elevates the industry from guesswork to building science. Cliff Budnick, who is the president of InOvate Technologies and a co-founder of the Dryer Vent Safety Council, sums this up perfectly in the source material.
What does he say?
He meets that proper dryer exhaust performance often involves more than just lint removal. The entire exhaust system should promote unrestricted airflow, using code-compliant materials from the transition duct through every turn to the exterior termination.
Unrestricted airflow. That is the key. Not just clean airflow, but unrestricted.
Exactly.
So if you're listening to this and you're thinking about your own home, you don't need to suddenly become an expert in anemometers, static pressure, or fluid dynamics. The takeaway here is actually very simple.
It really is.
The next time you hire a professional to service your exhaust system, you really just need to ask them one specific question. How do you measure dryer vent performance before and after service?
Right.
If they just hold up a wire brush and a camera, you know they're only checking the condition. But if they can explain their pressure or velocity testing process, you know you're dealing with someone who understands performance.
I think there's a broader context to leave everyone with today, especially as we think about how homes are evolving. We live in an era where we expect everything in our houses to be incredibly smart and data-driven.
Oh, totally.
Our dryers have microchips. They can literally text our phones when our clothes are dry or when the moisture sensors detect a specific humidity level.
Yeah, my washing machine connects to Wi-Fi to download custom wash cycles. It's crazy.
Right. We have completely normalized, high-tech, highly calibrated appliances.
But the infrastructure they rely on is stuck in the past.
Exactly. When it comes to the vital exhaust systems that keep those expensive appliances safe, functional, and efficient, we still tend to treat them as dumb, static, invisible tubes.
We just assume that if the tube is empty, everything's perfectly fine.
But as our homes and our appliances continue to get smarter and more precise, shouldn't our expectation for measurable, dynamic performance tracking in our home's hidden infrastructure evolve too?
That is such a good point. Why put a supercomputer appliance on a fundamentally broken freeway? It just doesn't make sense to upgrade the machine without verifying the road it travels on. Well, thank you all for joining us on this deep dive into the physics of your home. Keep asking the right questions, demand data over assumptions, and we'll catch you on the next one.